I think we should move on to our next speaker, which is Professor Tom Herring. And he's a full professor at MIT from the USA. And he has been focused on high precision GPS studies and relevant geophysical applications. So he has received plenty of prestigious awards from IAG, AGU, EGU, and NASA. I think many of you here from the audience list should know Professor Tom Herring, because most of you guys have used the GAMIT software in your professional career. So let's welcome Professor Tom Herring to give his talk on the BDS network analysis in GAMIT.
Well, thank you very much for that introduction. And this talk's given by myself and Mike Floyd, who's a researcher at MIT, and Soren Nistor, who is from Romania, who has done some of the analyses for this work. So what I wanted to talk about today was just an overview of how we've implemented BDS in the GAMIT processing, and then show you some results. And there's two sets we're going to show. One is from 2021, which is using the IGS 14 phase center models. And for this processing, we are keeping the orbits fixed based on the code, the European code Center for Orbit Determination in Europe, keeping their orbits fixed. And this is from March of 21 up until June 30th of 2021. This is when the full BDS 3 and BDS 2 systems are both available. So we have typically 37 satellites per day in the processing. And then finally, we'll look at the 2022 processing. And this is IGS 20 phase center model, which has just been released. And this is part of our ongoing operational processes. We're doing the trial testing for the IGS 20 adoption, which will happen at the end of November. And so this is full processing using the MEO and the inclined geostationary orbit satellites. And this goes from August 7th of this year up until September 9th, which was just a couple of weeks ago. And again, this is part of our operation. We're still working out how to do this. So in the GAMIT processing, firstly, GAMIT itself has been around since the 1980s, was initially designed for the GPS system, and was extended to multi-GNSS, starting with version 10.61 back in 2017. And as we learned more and more about the multi-GNSS constellations, 2018 and 2020 were releases that allowed us to do better processing of Galileo, Beidou, and in 10.71 to bring in the GLONASS, which is the frequency switched system, which is quite different to the other GNSS systems out there. Now, still in GAMIT 10.71, we process each GNSS system separately, and we do dual frequency processing. And then the different GNSS systems are actually combined into a single solution in which station coordinates, mean atmospheric delays at stations that are common, Earth orientation parameters are shared between the systems. And we do that with the program called GlobeK. Now, GlobeK allows us a fair amount of flexibility in here. The nominal solution would have the station coordinates be the same between all systems. But for test experiments, we can also allow different station coordinates for individual stations for different types of constellations. Certainly our work with the Galileo system has suggested that there is some systematic differences in coordinates. And that's probably due to our not complete phase center model, which I'll come back to later on. And then finally, in the GlobeK solution, when we're doing orbits, we actually use a smoothing Kalman filter for a week of data, typically, in which the radiation pressure parameters that we're estimating can be treated stochastically with day-to-day constraints applied to them to help smooth out the orbit determination. So specific to the BDS system, we do dual frequency processing, which again, something that will evolve with time. We use B1, which is the 1561 megahertz channel as the default. That is L2 X and C2X, where the X depends on the exact tracking mode. We have a hierarchical list of IQ, X, and DPZ, which is the RhINX3 standard names. And depending on what's actually in the receiver, we choose different ones. Our default for the second lower frequency is the B3 frequency, which is at 1268 megahertz. In the RhinoX3 is L6 and C6. And again, the X depends on that. In our processing, we can also specify a different lower frequency if we wish to. And we do this for both Galileo and actually we do this with all constellations, which now have typically 3 frequencies available. So our other one is B2, which is the 1207 megahertz channel. That's L7 and in the RhinoX3 standards. And generally, that is poor performance at the moment due to the limitation availability on BDS2 only. We can also do P2A, which is the 1176 megahertz, which is L5. And again, that's only available on the BDS3 system. So we found the using the B3 channel gives us the most numbers of stations and the highest quality results. For orbit modeling, we use 6 integration constants for each satellite. We have 3 constant radiation pressure parameters, and then once per revolution terms, which we apply to all 3 axes, the direct, the y-axis, and then the orthogonal b-axis. We also have 2 and 4 times per rev terms in the direct radiation force. Now, we estimate all of those in the phase processing, but that's a very loose orbital solution. And so when we propagate the system into the globe K system, we typically force a number of those parameters to just have 0 a priori contribution. And then we use orbit overlaps and the estimates and their uncertainty themselves to determine which satellites require more than the standard number we use, which is just the constant terms, the once per revs in the b-axis direction, and then twice per rev in the direct radiation forces. Now for BDS at the moment, we have no albedo model and we have no antenna thrust model. And the other complication is in the phase center offset models in both IGS 14 and IGS 20 antex files, there is no nadar dependence on the phase center variations. And we certainly know from the GPS days when there was no nadar dependence in the models that when that was implemented, there was like typically 10 centimeter changes in ground station coordinates. So later on in this meeting, we will actually see, I believe, a phase center model for the Beidou satellites, which we're looking forward to being able to implement in our processing. So for our specific 2021 processing using the IGS 14 system, we used 119 stations, and these are the distribution over here. The blue dots are the Beidou stations that were used, and then Brux and SOD3 are just 2 stations I will show time series for. And so we have good coverage over most of the world, although I will note in publicly available data, we actually have very little data available in China itself. And so of these 119 global stations we use, 77 contained BDS data. And again, code orbits were used. So this is a somewhat small figure, and I'll give you the numbers at the bottom of the most critical. For this interval of time, we've processed GPS, Galileo, BDS by itself, and then the combined Galileo, BDS, and GPS systems. And so for GPS and Galileo, we're typically running about 1 millimeter in the horizontal RMS positions, 4 to 5 millimeters in vertical. And we know for Galileo, there still seems to be some inconsistencies in the PCO models, at least compared to the GPS and system that we have. And then for BDS, it's around 2 millimeters, about twice that size. And again, there's a number of outliers in here. And I think one of these is associated with the phase center models for some stations not having all frequencies available. And so our default is to drop back to the GPS L1, L2 phase center models when that is the case. And I think that's what's corrupting some of these solutions. And then overall, the full combined solution actually is a little better in the horizontal components than the individual solutions, which is a good sign. The vertical is degraded a little. And again, I think the phase center models tend to affect height more than horizontal components. And that's part of the issue. This just gives you a sense. This is actually one of the better stations, but this is SOD3, which is in Northern Europe. And again, blue here is the GPS coordinates. Black is the Galileo, and then the brown ones are the BDS solutions. We see some issues when we start. Again, I think we're still looking at some of the data quality issues here. And there does seem to be a little bias between BDS in the height and the Galileo systems. And again, given the phase center models, that's not unexpected. Brux, we just chose because it actually has an anomaly here at this time. Outliers, which are actually about 10 millimeters in the north component at this station. And the good sign here is that all of the systems see that same anomalous behavior at that time. So this appears to be something physical happening at the station, or an atmospheric modeling problem potentially that's common to all stations. We also see a small little offset back here at 21.3, which is also seen by all of the systems. So clearly these multi-GNSS systems are seeing many things similar. And again, we've done some editing of large outlier points. For our global processing, we're doing this for the IGS 20 testing phase, and we've run from weeks 2222 to 226, which is August to September. Again, this is our standard MIT processing. For the inclined geostationary satellites, the way our algorithms are working, because of the poorer overlaps in those orbits, we are actually estimating the once per rev direct and 4 times per rev direct pressure radiations on those forces as well. And again, we are still looking at precisely how best to do these orbits. And again, the PCOs are again an issue where there does seem to be an issue in this processing of the phase center models not being consistent with what our software seems to want. And again, this is a network processed across here. It's 350 GPS stations. And of those, about 190 have BDS data available. And you can see we get a nice global distribution of sites for Europe and North America and various places around the world. So for this particular processing, this is now, again, just the weighted RMS fits of the horizontal position determinations. So BDS final is using the BDS system. We actually have the phase center offsets estimated bi-weekly amounts for this solution. And so that's around 3 millimeters in the north and the east, 10 millimeters in vertical. Our Galileo final solution is 1.5 and 1.7, and then GPS is 1.2 and 1.28 millimeters. Now, these solutions, which are labeled final here, those are with full stochastic orbits. The group below is individual daily solutions in which the orbits are not tightly constrained. They're loose orbits. For Galileo and GPS, we'll see the quality of the fits are very similar there. But you'll notice for BDS that when we have the PCOs fixed and daily orbits, the quality decreases. And so that's, and certainly when we estimate, look at the values of the estimates, we see up to meter level changes in the PCO values for the BDS satellites. And again, when we do it free in these daily solutions, things actually improve considerably over when we have it fixed. And again, just to give you some ideas of time series here, this is the Alice Springs site in the middle of Australia. And again, we see some small biases. This is 5 millimeters in the east components and in the heights. We also see some changes in quality that we're still looking at in terms of data processing. And this is the Brux site back in Europe, again, the same one we looked at before. And again, we see for much of the time, it's quite good. At the end here, in that last week, we've just processed, and again, we're not certain why at this point, the quality of the BDS solution seems to degrade, and that's not clear yet. Again, we're still developing this system and trying to understand how best to do orbits with this system. So just in conclusion here, the GAMIT BDS processing, we are missing some critical metadata for the BDS satellites at the moment. As I said, the phase center models have no native dependence to them. There is different frequencies. There is values for the PCOs for different frequencies, but we do seem in the IGS 20 system in particular, we seem to be seeing fairly large adjustments to those. There's no albedo or antenna thrust models available. The yaw model is a potential issue here. We're currently using one which is normally based on our GPS model, and I believe a new YOR model has been released for the BDS system, and that we will implement soon. And as I pointed out, we do actually have a lack of coverage over China for stations that are openly available to the public, and as a result, the IGSO satellites orbit determination is probably suffering because we're missing a fairly large part of their arc with a large number of stations available. And again, one thing to be cautious of is the PCO estimates we're getting at the moment, we know from earlier studies, certainly can be affected by the radiation force modeling as we in the processing. And again, we do have some stations where the phase center variation models at the antennas are not available at all frequencies. We know that's an issue with Galileo as well. And so we're still looking at that to see how that affects our radiation, our effects. And finally, GAMIT 11, which is currently being developed, the intention here is to process multi-GNSS at the phase and range level for all satellites simultaneously. And we're currently using the lessons learned from the Constellation processing to guide this development. Thank you.
All right, thank you, Tom. This is a very interesting talk. Any questions for Tom?
Yeah, I can see stuff coming in the thing.
Okay.
Is there any tests made over Africa? Please share, especially using GAMIT. We do have African stations in the solution. We haven't looked carefully at their performance yet, but certainly our global processing for the IGS 20 system, all of those results all go to the CDDIS and are publicly available. So people can download our processing results, our SINEX files, and look at the quality exactly as they plan to. We're going to ask a question. Oh yeah, raise hand. Okay, that's that. Okay, that seemed to, let me just stop share for us. Dear Professor, oops, I got the beginning of it. Oh, that's Uganda.
And more?
Yeah, I think when you do the chat, I always have this problem myself, is you often type a line, you hit return, wanting to type more, but then it actually sends the chat message on. So maybe the person's just typing a little more. And maybe it's related to the African question.
Yeah.
Yeah, maybe we just go back to the global. So the global network, as you can see, certainly in much of Africa, we do have quite good coverage, and it is covered with BDS. So the triangles here, the little red symbols are basically GPS only. Anything which has a green triangle on it is Galileo, and then anything with a blue on top, that's the BDS sites. So yes, very southern part of Africa, we're not doing well. That's mostly all still GPS equipment rather than multi-GNSS at this point. Share something on the height in BDS. Yeah, not sure what that means. Again, with the phase center models at the moment, I think, which are, IGS 20 was developed basically for GPS, GLONASS, and Galileo. And so the incorporation of BDS is something which is now in process of happening. And so we're still learning a lot about it. The phase center piece, the next question was the PCVs. We do have PVCs, phase center variations for all the constellations except the BDS, which have 0 in them at the moment for the nadir dependence. That is, we're using a standard international IGS 20, what's called Antex file. And so far, we actually have not deviated from that. We do have the ability to go through and develop our own elevation nadir dependence models. We haven't tried that yet because we're trying to stay with the standards. And I think this is something which we may hear more about later on. In fact, I know there's a talk later on this subject.
Any more questions? For Tom, I think this is a very good chance for you to communicate closely with Dr. Herring.
Okay. Well, thanks very much.
Okay, thank you. Thank you, Tom. Thank you for your contribution.